We use it every single day, practically every single second. But have you ever stopped to think about how the internet actually works? Well, today we're going to pull back the curtain and follow one little piece of data on its incredible journey across the world. Let's dive in. You click a link, you hit send on an email, and then magic, right? Something happens on the other side of the planet almost instantly. But what is that magic? What's the actual journey your data takes in those few milliseconds? That's exactly the path we're going to trace. So let's start with the big picture. At its heart, the internet is just one giant, sprawling computer network. It's nothing more than a system that lets all our digital devices, your phone, my laptop, the server that hosts Netflix, talk to each other and share information. It's just a gigantic, interconnected web. Okay, so our data needs to travel. And just like us, it can't just teleport. It needs roads to get where it's going. This first part of our journey is all about the physical stuff, the actual wires and cables that crisscross the globe and connect everything together. These digital roads are probably things you've seen a million times. We're talking about the old school twisted pair telephone lines, the coaxial cable that brings you cable TV, and the real powerhouse, fiber optic cables. These things use light to transmit data, and they're basically the superhighways of the internet backbone. Now, just having a bunch of roads isn't enough, right? You'd have chaos. You need a map. In networking, that map is called the topology. It's simply the design, the layout, that shows exactly how all the devices on a network are connected to each other. Let's look at a couple of classic layouts. First up is the star topology. It's pretty intuitive. Everything connects to a central point, kind of like the spokes of a wheel. It's super reliable, because if one spoke breaks, the rest of the wheel is fine. Then you have the bus topology, where every device just hooks into one single main cable. It's cheap and easy to set up, but it's got a huge weakness. If that main cable breaks anywhere, the entire network goes down. Then you've got these two. A full mesh network is the absolute king of reliability. Why? Because every single device is connected directly to every other device. There are tons of paths for data to take. The downside? It's crazy expensive and complicated. On the other hand, a ring is nice and simple. Data just gets passed from one device to the next in a circle. But, like the bus, if one device in that chain fails, the whole ring is broken. All right, so we've got our roads and we've got our map. But here's the next problem. What happens when multiple devices want to use the same road at the same time? You get a traffic jam. In the digital world, we need some rules of the road to manage this chaos. You see, when two devices on a shared line, like on that bus network we talked about, try to send data at the exact same moment, their signals literally smash into each other and get totally garbled. It's a jumbled mess, and we call that a collision. To prevent this from happening, networks use a set of rules called Media Access Control Protocols, or MAC for short. One of the most famous protocols for this is CSMA/CD, and honestly, the best way to think about it is like a very polite conversation. It's super simple. First, a device listens to the line. Is anyone else talking? No? Okay, cool. Then it starts to transmit its data. But, and this is key, it keeps listening while it talks, just to detect a collision. If it hears one, both devices immediately stop talking, wait for a completely random amount of time, and then one of them will try again. It's a brilliant and simple way to share the line fairly. Okay, we have the roads, the map, and the traffic rules. Awesome. Now, let's talk about the data itself. Before you can send a message, you have to package it up properly for the long trip ahead. And this is the job of what we call the data link layer. See, you don't just send a whole video file or a giant email as one continuous stream of ones and zeros. That would be a nightmare. Instead, the data link layer chops up your data into these nice, small, manageable chunks called frames. And this is absolutely crucial, because if one little piece gets an error, you only have to resend at one tiny frame, not the entire file all over again. Think of each frame as a little package ready to be shipped. It has three main parts. The header is like the shipping label. It has the physical MAC addresses for the sender and the receiver, the local street addresses. The payload, well, that's the good stuff, the actual data inside the box. And the trailer is kind of like a quality check seal. It contains a special code that helps the receiver know if the data arrived perfectly or if it got damaged along the way. So far, pretty much everything we've talked about is like sending a package to your neighbor down the street. It's all local. But what happens when you need to send that package across the country, or even across the world? For that, you need a whole different level of addressing. You need a global postal service. And here is the most important idea to really understand the internet. It is not one single massive network. It's a network of networks. Literally thousands, millions of them, all interconnected. Your home network is one, your ISP is another, Google has its own massive network, and they're all linked together. The job of the network layer is to navigate your data across all of them. To make that happen, a local MAC address just won't cut it. We need a global address, and that's the IP address. You can think of it like this. Your MAC address is like your house number on your specific street. It's tied to your physical device. But your IP address is your full global postal address. House number, street, city, state, zip code, country. It's what allows a device anywhere in the world to find you. Now, the original internet protocol, the one we've all been using for decades, called IPv4, uses a 32-bit address. With 32 bits, you can create a maximum of about 4.3 billion unique addresses. Back in the 1980s, that seemed like an impossibly huge number, more than we could ever possibly need. Well, fast forward to today. We have nearly 8 billion people, and many of us have a phone, a laptop, a tablet, a smart TV. You get the picture. How on earth do we not run out of addresses? Well, the short answer is we have. We've just gotten really good at using clever workarounds, and we're also in the middle of a very, very slow transition to a new system called IPv6, which has an almost unimaginable number of addresses. So the IP address on your packet is its final global destination. And at the intersections of all these different networks sit special devices called routers. A router is like a postal worker at a sorting facility. It looks at the destination IP address on a packet and says, okay, to get there, you need to go in this direction. And it forwards the packet along to the next router, getting it one step closer to home. Phew. Okay, let's take a quick breath and recap this incredible journey our little piece of data just took. I know it seems complicated, but it all fits together into a really beautiful, logical stack. What we've just done is walk through the first 3 layers of what's known as the OSI model for networking. We started at the bottom with layer 1, the physical layer, that's the actual cables in the network layout. Then we moved up to layer 2, the data link layer, which packaged our data into frames for local delivery using those local MAC addresses. And finally, we got to layer 3, the network layer, which used the global IP addresses to route that data across the entire internet. Every single click, every message, every video you stream relies on this incredible high-speed dance of physical wires, local addresses, and global routing. It's a system that was designed decades ago and somehow managed to scale beyond anyone's wildest dreams. But it makes you wonder, as we move from connecting billions of devices to connecting trillions of them, our cars, our homes, our cities, what new rules of the road will we need to invent for the internet of the future?